So today we're going to be going over problem 14.12 out of Introduction to Chemical Engineering Thermodynamics. The chemical reaction we have right here is N2 plus C2H2 goes to HCN, all in gas phases. Initially, it's an equimolar mixture of N2 and C2H2. Equilibrium is reached at 650 degrees Celsius and atmospheric pressure. T naught is set to be 25 degrees Celsius, so T is equal to 650, and it's assumed to have ideal gases. So with that, we're trying to find the composition of the system at equilibrium, and then we want to see if there's any effect of doubling the pressure. Going to the solution, our first step is to determine the standard heat of reaction. And we can use equation 1 right there. So it's basically just the summation of the moles times the heat of formation, the standard heat of formation of the products minus the summation of the moles and the standard heat of formation of the reactants. So it's products minus reactants, and then you see it more explicitly. And then the values for this and this can be given in table C.4. Plugging and chugging into the equation, we get that the heat of reaction is 42,720 joules. The second and third step are basically trying to help determine what G is. So we use this equation. So this long equation right here is in the book, and I believe it's equation 14.18. So we use this equation to find G, and so we sort of break it down in bits. So the first bit is this term right here, and it is written out explicitly to be that. So to get delta A, delta B, delta C, delta D, we use the heat capacity constants from table C.1. And again, it's kind of just like the heat of reaction, so it's just the summation. So the moles of the products times the A of the products minus the moles of the reactants times the A of the reactants. So right there, you can see an example of what the formula looks like. And then for each of them, you can see that it's like delta A is 0.06, delta B is 1.73 times 10 to the negative 4, delta C is 0, and delta D is negative 19,100, sorry. We also use the symbol tau in our equation, and tau is just the T over T naught in Kelvin, and so you can see that tau is just equal to that. We're filling out this equation 2 again right here. We can plug and chug our values that we found, and we get that this value is equal to, or this term is equal to 60.15 basically. Our third step is to figure out another one of the terms in the delta G equation. So it's then this last term down here. So this is the term we're trying to find. Here is the explicit form of it. And again, that's also in the book. It's given in chapter 14. So we use the delta A, delta B, delta C, delta D, and tau, all of the same ones in this equation. So we get this value for this term is equal to negative 0.122. And then our fourth step is to finally basically figure out what G is, or delta G. So initially we need to sort of do what we did for the delta H of the standard for delta G. So this is, again, just the same type of equation in the same table, C.4, and you just plug and chug to get delta G of the standard is 39,430 joules. So then you use delta G standard, delta H standard. You use your values from steps 2 and 3. So this 60 value and this negative 0.12 value. So you use those values, plug into here, this long equation, and you get that delta G is equal to 33,954.4 joules per mole. So once you find delta G, then you can use that to find K. So this equation right here is found in the book in chapter 14, again, right next to all the other ones. You plug delta G in, you plug T and R, and then you can get K is equal to that value of 0.01198. So once you find K, then you find epsilon. So epsilon is found from the vapor molar compositions of each. So basically the mole fractions of each reactant and product is given based on the coefficients in the normal chemical equation. So the mole fraction of Y is this, which is the same as mole fraction for C2H2. And so mole fraction of N2 and C2H2 are the same. And then the mole fraction of HCN is that right there. So then you have this equation right here, which is just the products, the molar fraction of the products over the molar fractions of the reactants. So you substitute your epsilon values into this equation to get this, simplify it down into this. And so you set this epsilon right here term equal to the K you found, and then you solve for epsilon. So epsilon is then equal to 0.05, roughly. And then the final step is to just find the composition. So we use these equations that we used in step 6, and you just plug and chug. So you put your epsilon in that you found, so just 1 minus your epsilon over 2 for your 2 reactants, and then your product is just epsilon. So your mole fraction of N2 is 0.74, mole fraction of C2H2 is 0.747. Wait, mole fraction of N2 is 0.47, mole fraction of C2H2 is 0.47, and the mole fraction of HCN is 0.5, roughly. And then since this was assumed to be ideal gases, we know that doubling the pressure would not have any effect on the equilibrium composition because they are ideal, and ideals don't get affected by